Hello. This presentation will talk about points at infinity and a little bit about projective space. This can be found in section 2.2.8, but also elsewhere. The topics are scattered around a little bit in the PDF. So let's start off with talking about points at infinity. So we're working in 2 space and homogeneous representations. So x, y, w represents x over w, y over w. And then the question should be, so far, we should say, so far we've had w not equal to 0. But we'd like to make sense of what happens with w equals 0. We're going to assume that at least one of x, y, and w is non-zero. But suppose that w is 0. So for instance, the question would be, what point, or what in particular, does 1, 0, 0 represent as homogeneous coordinates? So of course we can't just take 1 over 0, 0 over 0, because that's not a point. We can't divide by 0. But we can think about taking a limit. So we can look at, for instance, consider 1, 0, epsilon, as epsilon tends to 0, and we can see what happens there. So let's do this. Let me draw the x-axis is here. The y-axis is here. And, for instance, here is 1, 2, 3, 4, etc. And if we look at the point 1, 0, 1, that represents the point 0, 1, 0, right? So here's the point 1, 0 represented by 1, 0, 1. And if we look at 1, 0, 1 half, well, that represents the point 2, 0. And 1, 0, 1 third, that represents 3, 0, etc. So in particular, 1, 0, 1 fourth, we divide by 1 fourth, we get 4, 0, it represents there. So you can see it takes the limit of this process. The limit as epsilon tends to 0 from the positive side should be a point at infinity, if such a thing were to exist, but we'll just say we can define it to exist if we wish to. And where does this point infinity lie? Well, it seems to lie somewhere out the end of the x-axis, because as epsilon gets smaller, we're moving further and further out the x-axis, so the point infinity should be out there someplace. But wait, we only did epsilon positive. What if epsilon is negative? So, well, we have, here's negative 1, x equals negative 2, negative 3, and so forth. And the point 1, 0, minus 1 represents minus 1, 0. The point 1, 0, minus 1 half represents minus 2, 0, again, because we're dividing through by minus 1 half, and we get minus 2, 0. The point 1, 0, minus 1 third represents minus 3, 0. And again, here epsilon is now tending to 0 from the negative side, so we take the limit as epsilon goes this way. And we should end up with the point infinity at the other end of the x-axis. So the answer to this should be then, there's a point at infinity that essentially lies at both ends of the x-axis. In other words, it's the same point at infinity. So if you go out the x-axis all the way until you reach infinity, well, basically you wrap around and you get to the same point at infinity as you would have been out the negative x-axis all the way until you reach the point at infinity. The same point. So it's sort of wrapping around the positive and negative x-axes are in the limit reaching the same point at infinity at both ends. Now, great. So that was a nice simple one where we're on the x-axis. Let's try another line here. So let's try the line y equals 1. So what point at infinity lays out at the endpoints of this line? Well, by analogy to the x-axis, it ought to be the same one at the positive end of this line as at the negative end of this line. But how does that relate to the other point at infinity? Well, here, for instance, is the if we take the point 1, 1, 1, this represents 1, 1. Because we divide through by 1, we get 1, 1. If we take 1, 1 half, 1 half, this represents the point 2, 1, because we divide through by the w value, the 1 half, and we get 2, 1. If we take 1, 1/3, 1/3, this should represent the point 3, 1, and so forth. So here's 1, 1/4, 1/4, and it represents 4, 1. So again, the limit here as epsilon tends to 0 plus in the picture here of 1 epsilon epsilon, right, is of course 1, 0, 0. It should be the same point at infinity at the end of this line as at the end of this line. So the moral here is that parallel lines all share a common point at infinity. So the moral, fit this in the bottom of the screen. Parallel lines have one and the same point at infinity. Let's push this a little bit and talk about the other points at infinity. So we just looked at 1, 0, 0. That's a point at infinity. What about 2, 0, 0? Well, this turns out to be the same point at infinity. Okay, and the reason for this is just that when we multiply by a scalar, we get the same, we represent the same point. So the general principle is that if we have x, y, w, and say alpha x, alpha y, alpha w, they both represent the same point. And this works both for points at infinity with w equals 0 and for actual finite points in the plane with w not equal to 0. Here we're assuming that alpha is not equal to 0. Okay. So if we took 2, 0, 0, it's also at the end, or both ends of the x-axis in every line parallel to the x-axis. Okay, what about, say, for instance, 1, 2, 0. Well, I'll let you work out this example here, but this is just at the end of the line. This is the point at infinity. At infinity on the line with slope 2. On the line y equals 2x, and every line parallel to that line. So every line parallel to that line, i.e. every line with slope 2. And I'll let you work out the pictures on your own, but the point is you can take the line, here's the line y equals 2x, and you can look at the representations of points. You know, here's 1, 2, 2, 4, and so on, and you can look at their representations in homogeneous coordinates and see that in the limit you can end up with 1, 2, 0. Okay. So what do we have here then is every family of parallel lines have one point at infinity, and it's in common. So this leads us to projective space. So two-dimensional projective space. So here we're getting to a new kind of geometry called projective space. We're all used to Euclidean geometry on the plane, but projective space can be viewed as a bit of a variation of that. We call it P2 rather than R2. And projective space, the points of P2 are the usual points of R2, the usual points in the plane, plus the points at infinity that we just discussed, namely one point at infinity for each family of parallel lines, or each maximal family of parallel lines. Okay, so the lines of P2, these are, firstly, there's the usual lines of R2, but now augmented to include their points at infinity. So we actually add an extra point at infinity to each line. And then plus, there is the line at infinity, which is the set of its members are the set of points at infinity. And so the picture here for what P2 is, it looks just like, P2 looks very much like R2, but we've added on somehow, I'll put a little circle here, of all the points out at infinity. Okay, so that's what projective space is in 2 dimensions. In 3 dimensions, it's also very similar to this. I'll do that on a separate board. The projective space for 3 dimensions is similar. So now the points of P3 are the points of R3 plus the points at infinity. Okay, namely, every family of parallel lines, or every maximal family of parallel lines, intersect at a common point in infinity. And these are the new points of infinity. We represent members of P3 with homogeneous coordinates. So in particular, this means that homogeneous representations are not unique. We multiply by a non-zero alpha value, we still represent the same point. Now the homogeneous points are x, y, z, w. They're 4 tuples, and they represent points in a 3 space with redundant notation. If you multiply by an alpha, you get another 4 tuple that still represents the same point. We now have P3 has a plane at infinity that holds all the points at infinity. And later on, we'll see uses for points at infinity when we get to Bezier curves and so on. At the moment, projective space points at infinity are more lurking in the background. We don't use them very much, except occasionally we'll use points at infinity to talk about directions rather than positions. So some of you may have had an art class or done a little bit of art, even in grade school, where you learned about points at infinity under another name. So artists use perspective in their images to make things look three-dimensional. Scenes look three-dimensional. And this gives them some notion of depth by making closer objects look bigger than further objects. We give the right sort of perspective that gives a sense of realism to an image. And they tend to use the notion of vanishing point. And a vanishing point is essentially a point at infinity, but drawn at a finite point on the image. So an example of this would be where you have a road. Here's a road extending out, and it's going off to the horizon, and so we just sort of let it draw that straighter. And it, at some point out here, intersects at the horizon. So picture this long road, and looking down it looks like the perspective that eventually it meets at some perspective, and we have meets at some common point. And this is the so-called vanishing point. And then to make the perspective look correct, the artist has to ensure that every other line that's parallel to the sides of the road also points to the same vanishing point. So if the artist builds a house next to the road, they would do it something like this. Here's the front of the house. And you would arrange that the base of the house is pointing right to the point of infinity, and the top of the house is pointing right at the top of infinity. If there's a back side to the house that's parallel to the front side of the house, then the line at the back of the house should also point to the same point of infinity. If there's a front door on the house, the horizontal front door on the house should also point to the same point of infinity. And in this way, you get the right sense of perspective. The next building over would have the same sort of properties. Any line on the structure that's parallel to the sides of the road should point to the same vanishing point. So it's a simple technique to put perspective in. Now, artists actually do something much more involved in this, also looking at perspective on other families of parallel lines, which I'm not going to try to draw here. This technique, if you look on Wikipedia, it'll tell you it goes back to the 14th or 15th century, so not that long ago, only about 500 years did this get used in a really systematic way in art. In actuality, you can go back, if you go to see some of the really old frescoes in Italy and so on, you'll see perspective in older pictures going back at least to the 13th century. So this has been around for, at least some portions of this work have been around since about 600 years or so. But it got codified in art about 500 years ago. Nowadays, the computer just does everything with matrices, and you automatically get the perspective because we're doing the right mathematics to place things in the right place on the screen. And that's it for this presentation. Thank you very much.